Welcome to another video for Stat 212. In this video, we're going to be looking at conditional probability, and specifically, we're getting into what happens when we're working with dependent data and how that affects our calculations when we're looking at intersections. So in the last video, we looked at what happens when we're looking at independent events and calculating probabilities, which is pretty straightforward because the probabilities remain constant no matter which path we go down, meaning that this probability is going to remain the same regardless of what happens in this other event. But when we have two variables or two events that are dependent on each other, we have to be careful because the probability of one is going to change depending on what happens with the other. So here's a question to add some context. Let's say that we have 200 people surveyed, and two of the questions they answer are, number one, do you have a gym membership? And number two, do you tend to have trouble falling asleep? And it turns out that these two variables have some dependency, meaning that people who go to the gym are more likely to fall asleep well, whereas people who don't go to the gym are a little bit more likely to have some sleeping issues. Now, it's not like completely stratified there where it's like 100% and 100%, right? But there's definitely a little bit of change in probability where if I know that somebody goes in the gym, then I know that their likelihood of falling asleep well is going to be a little bit higher. And if they don't go to the gym, I know that their probability of sleeping well will be a little bit lower. So I am going to kind of adjust that probability based on what I know about the other variable, and vice versa, right? So if I know their sleeping habits, then I can make a better prediction about their gym membership likelihood. So yes, I would say that there's a dependency in this data. And the way that we can kind of see that here is that the probability of, I'm going to say sleeping well, I'll just say good sleep, given gym. So let me actually, what I'm going to do, good sleep given gym, so given that they're going to the gym or they have a gym membership, is going to be 53 out of 75 there. Whereas the probability of good sleep given no gym is only 70 out of, it looks like that's about 125. So if I calculated these out, they're not like drastically different, but they're definitely pretty different. So this comes out to 0.707, and this other one comes out to about 56%. Now, if I'm assuming this is just a sample, right, then I'm only estimating these proportions. So maybe I shouldn't be so hasty to conclude that they're definitely dependent, but there's definitely a suggestion of dependence, right? So there's a big enough gap that I'm kind of left questioning if these events really are dependent now. But I suppose I should be careful and say that without maybe doing a statistical test first. I probably shouldn't jump to that conclusion confidently just yet. But the suggestion is definitely there based on those numbers. But in general, conditional probability is going to be this idea of looking at the probability of one thing based on knowing this other thing. So here's another example where conditional probability can kind of help us understand our data better. So let's say that we're looking at somebody's smoking status. And so if we just ask that question in this particular data set, so this is the data that we looked at, I believe it was in Chapter 3. We're looking at smoking data from the 1970s. And apparently about 44% of people in that survey said that they did smoke. However, if I also know that their age, I might better be equipped to do a conditional probability where I'm looking at their likelihood of smoking given their age bracket. Because in this case, there definitely seems to be a relationship between somebody's age and their smoking status, where generally people who are much older are much less likely to smoke in this particular sample, and people who are younger, especially kind of these middle-aged people, we see a much higher rate of smoking. So if I were to calculate the probability of smoking given an age bracket, I'd probably make a much better estimate of their smoking status than just saying, well, 44% of people in this sample smoke. I mean, that's still true, but I can kind of break that down further to understand more about my data and see that dependency between smoking status and age that we apparently see in this data. So if we're calculating a conditional probability, it's maybe a little bit confusing, but not that confusing, I don't think. We're essentially finding the probability of B given A. The notation we're going to use is B vertical line A, by the way. So whenever you see this vertical line in probability, we say given, or assuming this is true. So B assuming A is true. Now the probability for calculating that is going to be the probability of both of these events happening together divided by just the condition part. So if you think about it, the condition part is going to be like, assuming this is given, assuming that I can kind of narrow it down to this sector, what proportion of the time do we see B also included in that, given we're in this sector here? Another way to think about it when we're working with frequency data is it's really just the number of cases that fit both A and B divided by the number of cases fitting B. So we'll do some examples with that. But with that in mind, let's just kind of keep in mind how we would calculate probabilities, where we have a probability rule for if we have intersections, finding intersections for dependent events. It's going to be the probability of A times the probability of B given A. And here's kind of the reasoning for this. So if A and B are dependent on one another, then we can't just find the constant probability of B and tack that on because B is changing, right? So if A is true, there's now a new probability for B, or we need to update our probability for B now. So it's going to be A times the probability of B given that A happened. So again, that's kind of the thing with dependent events, is that the probability shift depending on whether or not we're assuming the first one is true or not. Okay, so we can demonstrate what that looks like with a tree diagram with the sleep and gym data table, right? So if I kind of use those probabilities that I calculated, again, they're really just estimates, but let's just say these are the probabilities. These really are the true things. And the probability that somebody has a gym membership is going to be 53. Actually, it's going to be 75 out of 200. So let's kind of recreate that here. So gym is 75 out of 200. No gym is going to be 125 out of 200. So that's also just going to be 37.5, 0.375, and that's going to be 0.625. So if we just kind of ask this first question, the likelihood that somebody has a gym ownership is about 37.5% in this particular population that we're sampling from, and it's going to be about 0.625 that they don't in this particular population. The next question we ask is if they're sleeping well or not. So we're going to have, again, two options of, I'm going to call them yes and no because I don't want to write out sleeping well or not sleeping well. And the thing is, this probability, though, depends on which way we go down. So it's not just going to be constant. I mean, there is a general probability that we could calculate if we wanted to. But if we know which way they went down, we really should adjust the probabilities to match that group. So if we're looking at the gym membership group, we know that it should be about 70.7%. So it's going to be about 70.7%, and no's they're therefore going to be about 293. Whereas if you're looking for the no gym group, that probability is going to be about 56%. So the probability of good sleep given no gym membership is going to be about 0.56. No is going to be about 0.44. So then if we want to calculate the probability that somebody, let's say that our question is the probability that somebody is not sleeping well given that they're going to the gym, that is going to be literally this thing right here. This is not sleeping well given gym membership. It's just going to be 29.3%. Another question that I could ask is, what is the conditional probability that you are sleeping well given that you don't have a gym membership? And that's going to be just this number right here. So 56% is the probability of sleeping well given no gym membership. Now, if I want to find the probability of an intersection here, then I would do, let's say I'm interested in the probability of gym and no, and that's going to be the probability of gym times the probability of no given gym. So then that's going to be 37.5% times this path of 0.293. So it's going to be 37.5% times the probability of saying no given. That's the way that we went down, 29.3%. And then I could calculate that, and let's say that I get 10.98%, or about 11% there. So we'll just round that to 11%. Okay, so kind of keep that in mind. The conditional probabilities are going to be the values that I'm writing over here. These are all conditional probabilities. Whereas the probability of an intersection is going to be going down a particular path and multiplying those probabilities together. They're dependent events because the probabilities change depending on which way we go. Whereas independent events, the probabilities don't change. This set of values would be the same as this set of values if they were independent events.